Thanks everyone so much for being here. I'm absolutely delighted to share from the ultraviolet perspective what I think to be some exciting challenges and exciting scientific opportunities for the line emission mapper. One point I have to make right off the top is to correct my friend Akash, who says that we have not detected the extended CGM for Milky Way type galaxies. We have long detected the CGM, extended CGM of Milky Way type galaxies, although not with quite maybe the grandeur and the beautiful picture that LIM could provide. So just to get things started, some notes on my talk today. So this will be very focused on UV absorption line studies. And so there's a rich growing body of literature on emission studies. This will just focus on absorption, and this is going back many before I was born, many decades work in this field. I'm just trying to focus here on key points that I think provide either opportunities for LEM to combine what we know in the ultraviolet and/or straight up pose scientific questions that I think a mission like LEM is essential to address. So many more opportunities absolutely exist, and I look forward to engaging with the ultraviolet community and others, anyone else who may have ideas to further establish our science mission and case. So just to make sure we're all clear on the experiment that I'll be describing for a large portion of this talk, and that is observing the circumgalactic medium using quasar absorption line spectroscopy. So the experiment goes like as follows. We have a distant quasar, background to a foreground galaxy to which we know its redshift. The two are close in projection on the sky. Therefore, the line of sight to the quasar probes the gaseous halo of this galaxy, and we can associate absorption lines like this at a particular redshift that matches the redshift of the galaxy. These are three species that we often detect in the ultraviolet at redshift 0, H1 Lyman alpha, the carbon-4 doublet, and carbon-2 at 1335 angstroms. So these absorption lines offer a number of observables that we can get straight out of the data, namely the column density, velocity centroid. For the cosmic origin spectrograph on Hubble, the velocity resolution is about 20 kilometers per second. We can centroid to small fractions of a pixel, small fractions of that. And then the line width indicating the thermal and non-thermal broadening. So what are some of these? This is a nice physical way to build some physical intuition about our various diagnostics, the spectral line tracers that we have in the far ultraviolet regime. So just some definitions to start us off here. The cool gas regime, what I'll call cool gas, is approximately 10 to the 4 to 10 to the 5 Kelvin. Between 10 to the 5 and 10 to the 6 Kelvin, I'll refer to that as the warm hot regime. So this phase space diagram, temperature plotted vertically, density plotted horizontally, shows the gas particles from a hydrodynamical simulation. I don't recall which one, but overplotted are the various spectral diagnostics that we have access to in the ultraviolet, starting with fairly low ionization species, carbon-2, silicon-2, and so on, all the way up through higher ionization species, oxygen 6, 7, and 8, and neon-8. Let's just focus on those ions of oxygen. So this is the same diagram with everything except oxygen 1 through 8 removed. So first, oxygen 7 and below, we have access to in the ultraviolet. Oxygen 7, oxygen 8, you have to go to the X-rays to observe these. So this is just showing where in redshift space we have access to these various tracers with the COS spectrograph. So as you can see, for a number of lines, we have adjacent ionization, or a number of elements, we have adjacent ionization states, but only at a select sort of range of redshifts. For some of our best friends, like oxygen 6, this coverage starts at about redshift 0.12. For neon 8, another ion I'll be talking about, redshift coverage starts at about 0.5. So here already we see an opportunity for LEM, which is to observe the warm hot gas tracers, namely oxygen 7, oxygen 8, and the others that have been mentioned so far in more nearby galaxies where we can actually study the properties of those galaxies in more detail. So just to make this abundantly clear, no pun intended, the ion fraction, the amount of some element that is within some ionization state changes drastically with temperature and density. So this is just showing those three upper ions of oxygen, oxygen 6, oxygen 7, and oxygen 8. And so you can see this is the ion fraction here as a function of temperature over this wide range of the warm hot regime and hotter gas phases. The dominant ion, dominant ionization state is oxygen 7 and oxygen 8, more so than oxygen 6. So this is log space here. Oxygen 6 peaks at about 25%, whereas you see nearly all of the oxygen is in oxygen 7 across a large swath of this temperature range. So this is the best, the best picture we have in terms of a mass census of the components of galaxies. So this is the fraction of mass relative to the expected baryon fraction in an L-star galaxy in the case of the bar chart you see on the right. So we have the contributions of the gas and the stars in the disk down here in the red and blue. And then you have the CGM components broken down by phase in the cumulative bars here. So the purple coloring represents the low ionization state gas. The warm hot that traced by oxygen 6 is in green, and then the hotter stuff is in yellow. So the solid colors denote what we feel to be conservative lower limits of how much of the contribution each of those phases makes to the overall baryon budget. So as you can see, we're confident of about a half of the expected baryon fraction, but those phases in particular, hotter than 10 to the 5 Kelvin, are highly unknown. These that would be traced by oxygen 6 for us in the ultraviolet, but can be measured, can be mapped directly by a mission like the line emission mapper. Even begging the question, are all-star galaxies baryonically closed, as is kind of suggested in this picture? Okay, now looking to kinematics. This is from the COS halos, a result from the COS halos survey, where plotted are individual absorption components of H1, neutral hydrogen, the relative velocity of those centroids of those velocity components to the redshift of the host galaxy. And they're plotted against the host galaxy halo mass, the total mass of the galaxy's halo, and color-coded by star forming in blue, passive in red. So those more massive passive galaxies, you can see relative to the escape velocities that are marked by these curves, occupy a much narrower velocity distribution, suggesting that these more massive halos, the gas that we're actually tracing in UV absorption, may be subvirial. So with the spectacular spectral resolution of line emission mapper, of course we can start to understand the velocity distribution of the hot gas, the ambient gas component that presumably these absorbers are swimming in across this large range of mass. Another puzzling result from the COS halo survey is this famous bimodality between star-forming galaxies and passive galaxies with regard to the oxygen 6 detected in the circumgalactic medium. So this is the column density of oxygen 6 detected in the halos of galaxies of various specific star formation rates. You see the passive galaxies here on the left in red. The blue galaxies are star forming. See a much higher detection rate or covering fraction of oxygen 6, much higher column densities of oxygen 6 in those star forming galaxies than in the passive ones. And so a number of models, including a lot of the including the simulations that Annalisa was just showing, have had some success in explaining this bimodality, but the explanations can differ wildly depending on the model. So line emission mapper, a huge advantage here will obviously be to measure kinematically, spatially, and the physical conditions, all three, the halos of these galaxies across star formation rate, halo mass, and of course mass starting from all-star galaxies. So we can do a little better in terms of studying the warm hot gas than oxygen-6, if from just a purely ion fraction standpoint. So this is the ion fraction of oxygen-6 across phase space, temperature vertically, and density across the x-axis. So the color coding here is the relative amount of oxygen that's in the oxygen-6 ionization state. So you see there are two regimes, that's collisionally ionized at relatively high temperatures, peaking at about 10 to the 5.3 Kelvin, and the photoionized regime, where you have to go to lower densities to get into this ionization state, but you can achieve this at much lower temperatures. This is the picture for neon 8. Again, we have to go out to redshift 0.5 to observe neon 8, but looking at these two, we can more unambiguously place gas that we would detect in neon 8 as being collisionally ionized, occupying this warm-hot regime, peaking at a higher temperature, whereas you have to go to much lower densities to also achieve to get to neon 8 ionization state at lower temperatures. So we've now been able to study neon 8 in such a way. So this is the first sample of circumgalactic neon 8 absorbers, and if we just make some simple assumptions about the neon 8 absorbers themselves and the gas that they're within in the galaxy halo, then we wind up with this photoionization. If the gas is indeed photoionized, this huge pressure differential where the gas is under pressured by 2 orders of magnitude. So this is a problem that occurs not only in this particular experiment with neon 8, but I think we really in the CGM community are starting to think a lot about pressure and the relationship. Is the gas that we're observing in hydrostatic equilibrium, and what are the dynamics of the gas? So I know I'm almost out of time, but I just want to make the quick point that the CGM is heavily influenced by galaxy environment, and we see a decline in the cool gas reservoirs of galaxies in higher and higher halo mass environments. And so being able to go down to the group cluster and galaxy group scale to observe the intragroup and intracluster medium, along with the CGM of these galaxies, will be, I think, a huge boon to understanding galaxy transformation as a function of environment. So I'll stop there, just list some of these opportunities that I've identified, and happy to take any questions you have.